So we are going to talk about L'Hopital's rule today. Now, way back, lots of videos ago, when we were first talking about limits, we used various techniques like simplifying complex fractions, uh, multiplying by the conjugate, factoring and reducing, and every once in a while I'd say something about, and if someone has told you about L'Hopital's rule, you cannot apply that yet. So I've very rarely mentioned anything about the indeterminate form because the indeterminate form is the format that lets you use L'Hopital's rule, which is the 0 over 0, typically what we would have seen. So I just stopped as soon as we got 0 in the denominator and said, all right, what are we going to do to make this to where we can utilize our old algebra techniques on this? But if you have the indeterminate form, which is 0 over 0, or infinity over infinity, and there's some other forms, but I'm not going to talk about those in this video, then we can use L'Hopital's rule. So this is that day that I said would eventually come, where I'm going to talk about L'Hopital's rule. All right, now let's kind of go back and look at where we were at that time. So what we had was something like the limit as x goes to 1 of x squared minus 1 over x squared plus x minus 2. And we would say, all right, can we just substitute the 1 in and see if this is in its domain? And you would say, well, let's see. 1 squared plus 1 minus 2. Nope, that's 0 in the denominator. And we would have said, well, maybe we can factor it. So this is x plus 1, x minus 1 over x plus 2, x minus 1. And these two x minus 1's cancel. So this is the limit as x goes to 1 of x plus 1 over x plus 2. And that would then allow us to substitute in x is 1. So you'd have 2/3, right? Now, what L'Hopital saw, and actually I've read that they're not sure that L'Hopital actually was the first one to see this, that actually it was one of the Bernoullis. But L'Hopital was the one that was, I guess, more well-known, okay, that came up with this concept. And so what L'Hopital was noticing is if you had two functions, and let's say that this is f, and let's say that this is g. All right. Now, if you blow these up, and I can only blow them up so big, but you can kind of imagine that right in this area right here, they act like a line. Remember, we've talked about linearization and differentials and tangents, and we've talked about all sorts of things where right in a particular area, you might be able to treat the curve as a linear approximation. Now, let's go back to here and let's talk for just a second. Now, f in that area where it's going to be linearized. Let me draw a picture. It sort of looks like this. So if we blew it up, really big in that area, it might look something like this. Right around this area here. So right around this area, that's what we're doing right there. Okay? So this could be theoretically represented by some line equation. If this is point A, And this one would have its own separate slope, but it's also at point A. So what he noticed that it's, if you took, let's call this y2. If you took the ratio of y1 and y2, then this would be the ratio over here. And these two reduce. So what you're left with is the ratio of the slopes, right? And we get the slopes from the derivatives. So it would be y prime of 1 and y prime of 2, right? So he was saying we can compare the slopes, the derivatives, and talk about the limits. If it's of this form where it's 0 over 0 or infinity over infinity. So let's see if that works for this problem. So we would go, all right, so the limit as x goes to 1 of x squared minus 1 over x squared plus x minus 2. If we substitute the 1 in, we would have 1 squared minus 1 over 1 squared plus 1 minus 2, which is this 0 over 0 form, which is indeterminate, right? So that says that I can apply L'Hopital's rule and take the derivative of, now, we are not doing the quotient rule, all right? We are not going to do the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. What we are going to do is take the derivative of the top separate from the derivative of the bottom, right? So the derivative of the top is 2x. And the derivative of the bottom all on its own is 2x plus 1. You okay so far? Now, let's think about this. If I just write equals, and you just happen to walk by and look over at my paper, you might look at it and go, those two things aren't equal. Okay, maybe the limits are equal, all right? You haven't proved that to me yet or anything, but maybe the limits are equal, but this x squared minus 1 and x squared plus x minus 2 are not the same as 2x over 2x plus 1. So I have my students, and some books use this, where they're going to put a little h right here that says, and I'm going to apply L'Hopital's rule and take the derivative of the top and the bottom, and that helps the reader to know what's going on. It may help you to keep track of what's going on because sometimes we're going to be applying L'Hopital's rule and sometimes we're going to be reducing. So in order to kind of keep track of what we're doing each line, it might help you to do that, but I am going to do that because it helps me. Okay. And I may wear on you, you may decide you're going to buy in. Right. Now what you do is when you apply L'Hopital's rule, you look at it again and say, okay, now can I make 1 be 0 and have this be in this variation of the function's domain and be not an indeterminate form? So let's try. It looks like if I put 1 in the top and 1 in the bottom, I'm not going to get zeros anywhere. And I'm certainly not going to have 0 over 0. So I just insert it in and go, all right, it's 2 times 1 over 2 times 1 plus 1. So it turns out to be 2/3. So can you see how you get 2/3 regardless of which way you do this? And depending on how good you are at factoring, this may be a good choice for you, but you can only apply it, right, when you've got this indeterminate form of 0 over 0 or infinity over infinity, all right? You can't apply it any other time. So let's talk about it for just a second. So if we have the limit as x approaches 3 of x minus 3 over x minus 4, this is going to be of the form, if you put the 3, substitute the 3 in, you'd have 0 on the top, right? And you would have minus 1 on the bottom. And that is not indeterminate. This is 0, all right? If you have the limit as x goes to 3 of x plus 4 over x minus 3, you'd have 7 over 0. This is not the indeterminate form, right? If you had the limit as x goes to 3 of x squared minus 9 over x minus 3, this would be 0 over 0. That is the indeterminate form. So you can only apply it when you have 0 over 0, not 0 on the top or 0 on the bottom. You have to have both. So let's look at the limit as x goes to 1 of x squared minus 1 over x squared plus x minus 2. Now, if you substitute in 1, you would have 1 squared minus 1 on the top, that's 0. You would have 1 squared, which is 1, plus 1 minus 2. This is 0. Actually, this is the same problem I did. Let's just not do this one again. That was not, it was entertaining, but it was not that entertaining the first time to do it again. Let's do something different. So let's do the limit as x goes to 0 of sine of x over the tangent of x. All right, so let's think. If I substitute in the 0, sine of 0 is 0. Tangent of 0 is 0. So this is the indeterminate form. So I'm going to apply L'Hopital's rule. We're using H for L'Hopital. All right, because it's looks like L'Hopital. Okay, and I've had some of my students misspell it and pronounce, and everything is La Hospital. Okay, so but it's L'Hopital, right? So the H stands for this part. So we take the derivative of the top separately from the derivative of the bottom. So the derivative of the top is cosine x. The derivative of the bottom, excuse me, is secant squared x. And we try and substitute in the 0 again. Well, cosine of 0 is 1. Now, as soon as you get a 1, or any number other than 0 or infinity, you know that you are not going to use L'Hopital's rule. So whatever you've got here, you're kind of stuck with. All right, now you can apply L'Hopital's rule several times, but as soon as one of them becomes not 0, all right, you can't apply it again. Well, let's see what secant squared is doing. So secant of 0 is the inverse of cosine, the reciprocal, not the inverse, the reciprocal of cosine. I'm showing my age because when we were first taught, they were called inverses. All right, so this is 1 as well. All right, so this is 1 over 1, which is 1. So the limit as x goes to 0 of sine x over tangent x is 1. And you remember from our discussion on limits before that we make a nice concluding statement, right, for our teacher. And for practice for our future jobs, where we learn to tidy things up and have a lovely summary like you do in English, right? Sometimes I think there's a little bit of competition where we just say, we want the same consideration that your English teacher gets. All right. Like I said, you just got to find humor where you can. So if somebody says, can you find the limit as x goes to 0 of this function? And you go, well, yeah, sure. Let's see if I can substitute it in. Well, 0 squared on the bottom, it's definitely 0. Excuse me. E to the 0 is 1 minus 1 minus 0 is 0, right? So this is 0 over 0. That actually didn't even look like a 1. All right. So I can use L'Hopital. So I take the derivative of the top. So the derivative of e to the x is e to the x. You would loop back in and take the derivative of x, which is 1. Okay, the derivative of 1 is 0. The derivative of this minus x is minus 1. And the derivative of 2x of x squared is 2x. I just already told you the answer. Now remember, you have to take the derivative of the pieces individually. Please do not get this messed up with the quotient rule, so that when you have to apply the quotient rule, which is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared, don't be applying L'Hopital's rule to the quotient rule. They're not the same, okay? And now you say, all right, can I use 0 now and get rid of the indeterminate form? So e to the 0 is 1 minus 1, and 2 times 0, well, this is still 0 over 0. So I can apply L'Hopital's rule again. So you can apply L'Hopital's rule several times. So the derivative of e to the x is e to the x. The derivative of minus 1 is 0. The derivative of 2x is 2. Now right here, I know I have a 2 in the bottom, so I cannot apply L'Hopital's rule again. And e to the 0, right, is 1. So this is going to be 1/2. And this is the limit as x goes to 0 of e to the x minus 1 minus x over x squared. There you go. Not too bad. All right, let's do the limit as x goes to pi over 2 of cosine squared x over 1 minus sine x. Now, when you do pi over 2, all right, cosine of pi over 2 is 0. So this is 0 squared over 1 minus, and sine of pi over 2 is 1. So this is 1 minus 1, which is 0 over 0. So I can use L'Hopital's rule. So I have the limit as x goes to pi over 2. Now, cosine squared x is actually cosine x squared, okay? So to take the derivative, you bring down the 2. You take the derivative of the inside. Okay, I'm taking the derivative of this. You bring down the 2, leave the inside alone, take 1 off the power. All right, loop back in and take the derivative of the inside, and the derivative of the inside is negative sine x over the derivative of 1 is 0, and the derivative of sine x is cosine x, so you have a minus cosine x here, because that minus was given. Now, if you look, do you see how this cosine x cancels out this cosine x? And this minus cancels out this minus? And you can do that, but this is not L'Hopital's rule. This is just simplification. So I have 2 sine x over 1, right? I don't know if you need me to show that 1 or not, but it's 2 sine x over 1. So this is no longer the ratio of a numerator and a denominator. This is just 2 sine of x, and sine of pi over 2 is 1. So this is 2 times 1. This is 2. All right. Now, sometimes I try to give you hints on what's going on inside of teachers' brains. Okay. Sometimes I'm sure you're kind of wondering, especially when it comes down to test taking. And I'll have students who go, do I have to show you these steps right here? Are those mandatory? And I'm like, no, they're not mandatory. You know, I don't know how I make mandatory a certain number of steps, but what I can tell you is that if you go straight from here to here, and I see no steps in between, and for some reason, unbeknownst to me, you came up with a -2, I'm not going to be able to figure out if you knew that there were negatives in the first place. I don't know if you remember to put this one in there. I don't know if you dropped that one off by mistake. I don't know where the error is. I just know this is wrong. And if this is wrong and none of this is here for me to look at, there is no partial credit. And so this would be all of the points taken off. because I have nothing that tells me why it's a -2. Did you just guess? All right. So if you want partial credit, you show me all the steps that you can, because then I would go, well, hey, they knew the derivative properly. They forgot the negative of, the derivative of cosine is a negative. They forgot that one, or they dropped one. So that helps me give you partial credit. But no, you don't have to show me all the steps if you're right. Okay. Now, here we go. Let's do another one. These are actually kind of fun, I think. No, I know. You don't have to say. All right, here we go. I can just see my students' faces now. All right. Okay. So you go, can I just put the -1 in here? So this would be -1 plus 2 minus 1. And this would be 1 minus 2 plus 1. So that's 0 over 0. So I can apply L'Hopital's rule. So this would be the limit as x goes to -1 of 2x plus 2 over 3x squared minus 2. Okay? And you would say, all right, now can I put a -1 in here? Okay, so 2 times -2, let's just run over here a minute. 2 times -1 plus 2 is 0. Okay, that's looking like I might do it again. And 3 times -1 squared minus 2 is 3 minus 2, which is 1. Okay, so I can't use L'Hopital's rule again. So the answer is 2 times -1 plus 2 over 3 times -1 squared minus 2. So it's 0 over 1, which is 0. As opposed to right, what if you have the limit as x goes to -4 of x squared minus 4x over x plus 4, right? Well, if you try to substitute this in, definitely you have 0 in the denominator, right? But in the top, you would have 16 plus 16, which is 32 over 0. This is not something that qualifies for L'Hopital's rule, right? It is not the indeterminate form. So way back, okay, in the first series of videos I made in this entire overall series of calculus, we talked a whole lot about limits. So if you just have stumbled onto this video by mistake, go look through the whole playlist, and there's a whole section on what to do with these right here. And you would go, well, I can factor the top, but that's not going to help me, right? Because this is x times x minus 4, and nothing's going to cancel. So no. And so what I called it then was that you're going to sneak up on it, because x plus 4 doesn't reduce out. It is a non-removable discontinuity. You are asking what's going on around an asymptote, a vertical asymptote. So what you have to do is you would have to treat this as what's the limit as x goes to -4 from the left. And what's the limit as x goes to -4 from the right of this x squared minus 4x, x plus 4, and x squared minus 4x, x plus 4. And I try to do it a shorter way than some books do. So it goes kind of like this. I just really want to know what's going on really close to -4. So if I'm trying to figure out what's going around -4, think of kind of a number line, right? To the left of it would be -4.001. To the right of it would be -3.999. So let's talk about to the left. So this would be something like -4.00, and you can pick however many zeros you want here. Just don't pick something like -5 or -4.5. Okay, get really close to -4 squared. Excuse me, minus 4 times a -4.001 over negative 4.001 plus 4. And I don't know, I don't care what the exact number is because this is something that's going to be racing off to infinity. So you don't want to tell me like 1,000 or 1,242 or whatever. I just need to know if it's running off to positive infinity or negative infinity. So what you're going to have here is this is some positive number after you square it, and this is going to be a positive number. So I've got a positive number on top, and I've got a wee little tiny negative number on the bottom. So any positive number divided by a wee little tiny negative number is negative infinity. So over here using that, remember we said to the right is negative 3.99. We say negative 3.99 squared minus 4 times the negative 3.99 over negative 3.999 plus 4 is a positive and another positive. So you have a positive over a wee little tiny positive and a positive number of some sort divided by a little tiny positive, and I'm talking about 0.0001 or something like that, is positive infinity. So the limit as x approaches negative 4 of x squared minus 4x over x plus 4 from both sides does not exist. Now, this L'Hopital's rule, it doesn't just work for two-sided limits. It actually works for one-sided limits as well. So if they asked you, something like this, where they're just asking for one-sided, you can still see if L'Hopital's applies and still apply it if it is applicable for the indeterminate form. So don't think that it has to be a two-sided limit. Now, what if we have some other forms, and some of the typical forms that you'll see is something like 0 times infinity, and that could be also 0 times a negative infinity, or it could be infinity minus infinity. And these are also considered the indeterminate form, but what we know is the ratio is that it needs to be 0 to 0 or infinity to infinity, not infinity minus infinity, because it's kind of like if this one's bigger, then my answer would be negative infinity. If this one's slightly bigger, then it'd be positive infinity. So it's kind of like, which one is it? All right. And well, let's not get into the 0. All right. So let's talk about what we're going to do. So let's say that we have the limit as x goes to infinity, and they don't have to go to infinity. They just have to result in that, of x cubed e to the minus x squared. All right. Now, let's talk about this. This x cubed, if you drive it off to infinity, it's going to be infinity cubed, right? It's huge. All right. Now this e to the minus x squared, do you remember that the e function looks like this? And so if you're on the negative end of it, right, then you're going to have 0. So what we're going to do is to say, well, this is this 0 constant infinity, but all I know is if I have a ratio. Is there some way to make this look like not a product, but like a quotient? Well, the easiest way to fix it would be that e has already got a negative exponent in it. Okay, so now we have the main one as x is going this way, this is going to be infinity, and so you would have infinity over infinity. So that's the form that I want, all right? So you have to sometimes manipulate products into looking like something is dividing into the other one, and then you can use L'Hopital's rule, all right? So I haven't used it yet, but I'm getting ready to. So L'Hopital's rule says I can take the derivative of the top, which is 3x squared, over the derivative of the bottom. So the derivative of e to the x squared is itself again, loop back in and take the derivative of the power. So it looks like this. All right. Now, let's look for just a second. So this x right here cancels out one of these x's up there. So this is the limit as x goes to infinity of 3x over 2e to the x. I'm not going to quite get that fitted in there. Over 2e to the x squared. Okay, so between here and here, I did not apply L'Hopital's rule. I just simplified it. So there's not one of those little box h's. All right. Now let's see where I'm at. As x goes to infinity, 3 times infinity is infinity, and I'd have 2, and e screams off to infinity. So I've got that infinity over infinity case. So I can apply L'Hopital's rule again, which says to take the derivative of the top, which is 3. Now at this point, you have 3 over something. I cannot apply L'Hopital's rule again. So whatever I get here, I'm going to have to figure it out. So I have 2. The derivative of e to the x squared is e to the x squared again. Loop back in and take the derivative of the inside. So this turns out to be the limit as x goes to infinity of 3 over 4x e to the x squared. Okay, so I can't use L'Hopital's rule anymore. So I'm just going to have to figure this out. So this is some sort of a positive number. And I'm going to literally have 4 times some huge infinity direction number times e to the infinity squared way out there. Okay, so this is a positive number over an absolutely huge number. Okay, so a positive number divided by an gargantuan huge number is effectively 0. Now remember, it started off looking like this. So this is our summary statement. So you can be professional. All right. Now let's look at the limit as x goes to infinity of x squared over x natural log of x, right? Now, this is interesting because this one starts off and says, let's just take one of those out. So this is the limit as x goes to infinity of x over the natural log of x. Okay? Now, as x goes off to infinity, obviously, that's going to be an infinity. The natural log function, goes kind of like this. So this one is going to go off to infinity very slowly. All right, but it does get there. I mean, certainly not as slow as the other one goes. All right, so, but it is infinity over infinity, so I can use L'Hopital's rule. So the limit of x, its derivative is 1. The derivative of the natural log of x is 1 over x. So 1 divided by 1 over x is x. This is not L'Hopital's rule. This is just a simplification. Need to tidy up just a little bit. And so as x goes off to infinity, so does it. All right. How about the limit as x goes to pi over 4 of 1 minus tangent x secant 2x, right? Now this If you substitute pi over 4 in, you get 1 minus 1. Tangent pi over 4 is 1. And secant of 2 times pi over 2 is secant of pi over 2, which is racing off to infinity. Okay, so you effectively have 0 times infinity. That's the form you're looking at. So this is also an indeterminate form, but I need to make it look like a fraction. So trying to take 1 minus tangent of x and moving it down would be 1 minus tangent x to the minus 1. That's not going to help me, I don't think. But secant, I can pretty well easily fix it by going, all right, this is 1 minus tangent x over secant of 2x is actually 1 over cosine of 2x, right? So this would be cosine of 2x right here. So now what I have, right, is the proper form, because this 1 minus tangent x is 1 minus 1 still, which is 0, and cosine of 2 times pi over 4 is cosine of pi over 2, which is 0. So now I've got that 0 over 0 form. So I've managed to move it from 0 to times infinity to 0 over 0. So this turns out to be, using L'Hopital's rule, and the derivative of 1 is 0, and the derivative of negative tangent is negative secant squared. And the derivative of cosine 2x is negative sine. Leave the inside alone, loop back in and take the derivative of the inside. Okay? Now, secant squared of x is, okay, let's back up a minute. Cosine of pi over 4 is the square root of 2 over 2, right? So secant of the pi over 4 is 2 over the square root of 2, which is the square root of 2, right? The square root of 2 cancels into that, leaves 1 behind. So this one is going to be the negative square root of 2 squared over the negative. All right, and what we're trying to decide is sine of 2 times pi over 4, right, is 2 times sine of, well, I've got this too. We're going to come back to that too. All right, let's just put it down here so I don't forget it. And 2 times pi over 2 is sine of pi over 2. And sine of pi over 2 is 1. So the negatives cancel. And the square root of 2 squared is 2. So you have 2 over 2. So the answer is 1. So the limit as x goes to pi over 4 of 1 minus tangent x secant of 2x is 1. Doing okay? All right, 2 more. Okay, so let's try these last 2. So I have the limit as x goes to 0 of 1 over x minus 1 over e to the x minus 1. Now as x is 0, right? And you're getting close to 0. You don't actually have to get to 0. So this x down here is getting closer and closer to 0 by like 0.1, 0.01, 0.001, 0.0001. So as you divide by progressively smaller numbers, you're going to get infinity, and you're going to get infinity here. So it's going to be one of those indeterminate forms. But the only way I have to work with it, with L'Hopital's rule, is if it looks like a fraction. So can you kind of see where we're going to go with this, where I've got 2 fractions? Is there a way to make it be 1 fraction? Because the only thing I have going for me in my little toolbox is if it's indeterminate of 0 over 0 or infinity over infinity. So I'm going to try to make it be one fraction. So they would need a common denominator, right? So you would have e to the x minus 1 over x e to the x minus 1 minus x over x e to the x minus 1. And I'm just insistent on making this minus 1 be a part of the power. All right. There. You okay? Now that gives me my common denominator. So I have e to the x minus 1 minus x over x e to the x minus 1. There needs to be parentheses around here. Got hung up on my minus 1s and dropped off parentheses. All right. Now, let's see where we're at. As x goes to 0, e to the 0 is 1 minus 0 over 0 times whatever, doesn't matter. It's 0, so that's going to be fit for L'Hopital. So I'm going to apply L'Hopital here. So the derivative of e to the x is e to the x. The derivative of minus 1 is 0. This is minus 1, the derivative of x. And the bottom is the product rule, so it's the first times the derivative of the second plus the second times the derivative of the first. All right? And when you check this, then you would have e to the 0 is 1, so this is 1 minus 1. This is 0 times 1 plus 1 minus 1. Okay, so this is going to still be 0 over 0. So here we go again. So the derivative of e to the x is e to the x. All right. This, again, is the product. Actually, you know what? Yeah, we're going to do the product rule. All right. So we would have the first times the derivative of the second plus the second times the derivative of the first plus the derivative of this, which is e to the x, and the derivative of minus 1 is minus 1, right? So I can actually, I think, factor out an e to the x times 1 plus, well, that was actually 2 of these, okay, plus, try this again, x plus 1 plus 1. So this is actually e to the x over e to the x, x plus 2. And these cancel. So it's the limit as x goes to 0 of 1 over x plus 2. Okay, and when x is 0, you have 1 over 2. So the limit of 1 over x minus 1 over e to the x minus 1, the limit. Try this again. 1 over x minus 1 over e to the x minus 1. Something like this. That's pretty bad writing, isn't it? All right, well, hopefully you've gotten used to my writing by now. All right, one more. All right, the limit as x approaches 2 from the right of 8 over x squared minus 4 minus x over x minus 2. All right, let's see what we've got. Now, as you approach 2 from the right and you've got something like 2.001, this first term is 8 over a little tiny number, right? So that's going to be infinity. And on the second one, it's going to be infinity as well. So this is an indeterminate form, but the only thing I can do with L'Hopital's is if it looks like a fraction. So I'm going to try to get a fraction out of it. So I'd have the limit as x goes to 2 from the right. And when you get a common denominator, right, because you would multiply this fraction top and bottom by x plus 2, all right, you would get 8 minus x squared minus 2x over x squared minus 4, right? Now this looks like it has possibilities. So let's factor out a negative and we'd have x squared plus 2x minus 8 over x squared minus 4. So this is the limit as x goes to 2. You'd have minus, this is x plus 4, x minus 2 over x plus 2, x minus 2. So these cancel. Of minus x plus 4 over x plus 2. And when you substitute that 2 in, you get minus 3/2. Okay? Now, if you had had this part right here, came over here, you'd have the limit as x goes to 2 from the positive side of minus 2x plus 2 over 2x. Okay? And so this is not 0 over 0 because I applied L'Hopital's rule here. Okay? So then when you substitute 2 in, you'd have minus 2 times 2 plus 2 over 2 times 2. This is minus 6 over 4. This is minus 3/2. So this technique here is really factoring and reducing. This technique over here is using L'Hopital's rule, and you get the same answer twice, right? So I hope this clears up a little bit about L'Hopital's rule. Just remember that what you're trying to do is to manipulate it, if it isn't already, into a fraction where you have 0 over 0 or infinity over infinity. And then you apply L'Hopital's rule until one of the items, the top or the bottom, is no longer of that form. And then you have to stop and figure out where you're at because you can't apply it anymore. But do just take the derivative at the top independent of the derivative at the bottom. Don't apply the quotient rule, and don't apply this to the quotient rule. Okay? All right. See you in the next video.